Oh man, guys, I wish you could see the contraption I built to hold this video camera, or phone rather, for you guys to see my work right now. You might fall off at one point, but we'll see how this goes. Alright, well, welcome to the video response to question 20 of chapter 21 of Physics 3 in Bensky's class. This question states that a 7.7 nanocoulomb and a negative 3.5 nanocoulomb charge are placed 18.5 centimeters apart. Where can we place a third charge so that it experiences no net force? Well, there's a couple things I would like to do right off the bat. First, I'd like to make some conversions, and we can call this nanocoulomb. We know that nano is 10 to the negative 6, so we can do 7.7 times 10 to the negative 6th, and negative 3.5 times 10 to the negative 6th. Those are two conversions I want to make right off the bat, and then also we can convert our centimeters here. We don't use centimeters in our Coulomb's law equation, so we're going to convert that to a 0.185 meters. Okay, well, more or less what this question is asking is, where can we place a charge around two fixed charges such that it experiences no net force? So there's kind of three orientations we can imagine. We can imagine first, let me make sure you guys are still in the video here. Alright, we can imagine first a positive charge all the way on the left. This is kind of how my thought process went about the problem first and at the very beginning. And a fixed charge all the way on the right. And I imagined that somewhere in between, another charge would float and stay in equilibrium, experiencing no net force. So I tried to imagine this, and I threw another charge in here, say that's right there, and kind of imagined what the forces would be doing around this charge. We know that this negative and negative force will repel each other, so if this is fixed and this is fixed, then we know that this charge will be experiencing a force to the left from this negative charge over here, and it will be experiencing a force of attraction again to the left by this positive charge. So overall, this charge will tend to move to the left because it's experiencing attraction on the left and repulsion on the right. So overall, it's going to force it to the left. Another way we could kind of imagine orienting these is putting two fixed charges. We'd put a kind of a positive fixed charge in the middle and a negative fixed charge on the right, and trying to bring in another charge. And I want to make note that I made a negative charge, but really it doesn't matter. The sign of the charge is irrelevant because, I mean, if you guys play around with it a little bit, you'll see that it'll repel and attract just the same. So yeah, there's still only these three configurations that you can do with a negative or positive charge. So the other configuration we could try is putting the negative charge over here. It will be attracted to this positive charge, so it will tend to move this way and experience a force in that direction, and it will be repelled from this negative charge, so it will be pushed that way. So this is interesting because we have opposing forces. But now we need to remember that our positive charge is larger than twice the magnitude of our negative charge. So if we bring this over here, it's going to be attracted to this positive charge, and that'll be a very strong attraction, and this will be a very weak repulsion. So this will come over here, and that'll be magnified by the fact that this R value, the distance between these two, is very small next to the positive value. So I think this one won't sit in equilibrium either. The last scenario we can imagine is two fixed, the negative and the positive fixed together like so, and the negative last charge being brought in all the way on the right hand side. This could just as well be a positive charge, but the premise of this setup is that this positive charge is very large, so its force will be greater in this direction, but lessening as it reaches over here, while this force is much smaller because the magnitude of this charge is lesser. So the idea with this one is this negative charge will be attracted by this positive charge, so we'll tend to feel a force towards the left, while this negative charge will be repelling it. So it'll be pushing towards the right on this last charge we add. Now imagine putting in a positive in there. Could just as well be a positive charge, doesn't matter. Still there will be a small attraction here and a large repulsion, so kind of just switch the signs on everything, or switch the direction of the attraction and repulsions. And so now we can kind of imagine that getting really close towards with this as a positive charge now, getting really close towards this negative, there's going to be a stronger and stronger attraction. But also getting closer towards this larger positive charge, there's going to be a repulsion. So it could fall in here and sit somewhere in between here. So we're gonna investigate that orientation. So let's call this value here our 0.185 meters. And we know that that's the distance between these two charges. So we'll go ahead and annotate that. And then this other distance we're just going to call some r value, which we're going to end up solving for. Okay. So another thing that's important to note is that this linear configuration is the only way to go about this equation, because if these charges were placed in a triangular or any other configuration other than linear, then this charge, as you can kind of imagine, will be attracted in this way or repelled in this way. It won't be able to fall into an equilibrium because these two forces aren't in line. So we need these two forces to be in line to kind of balance out this third charge we're placing. All right, now pushing forward. So one kind of old physics idea that we need to get in touch with before we really start this problem is the sum of the forces equation. And we know that on this guy, the sum of the forces from the positive and negative charge are going to equal 0 on this body over here, because that's what's going to keep it from moving anywhere. And also our question asks that there's no net force. And so net just means the sum of the forces. We're really going to utilize this idea so that we can cancel out a couple things in a couple minutes. Then the equation that we're going to be working with is the Coulomb's law equation, which we remember as force equals K, our constant, times Q1, which is our first charge, times Q2, which is our second charge, all divided by the distance r squared. So that's the distance from its other charge. So with this sum of the forces things, we can do something cool, and that is that 0 must equal this force plus the other force. So K times Q1, and the force is experienced on Q3, so we're going to go ahead and multiply by Q3 and divide by the distance from Q1 to Q3, which is this distance 0.185 plus r. Then we're going to square that whole distance. And then we're going to add that to this other force that we're experiencing. Sorry, I'm kind of running into my own numbers over here. Don't forget about that guy for now. Which is K, again, times Q2 this time, because we're focusing on this force, times Q3. Now Q3 is going to be in both equations. Then that's because that's where the forces are being felt. So we're going to have to bring up that force in both equations, because those are the two that are kind of balancing each other. So to clean this up a little bit, and notice I just put r squared on the denominator of this one because this distance is only r squared. So to clean this guy up a little bit, we can bring over one of these equations to be a negative on the other side, and they'll cancel each other out. So we can do negative K times Q1 times Q3 divided by 0.185 plus r, all values squared, equals K times Q2 times Q3 divided by r squared. And then we can cross multiply, and once we do that, I'll show you guys a couple things we can use to clean up this equation. So we'll do r squared, when this is just bringing this guy across this way and this guy across this way, times k times quantity of q1 times quantity of q3 divided by 0.185. Oh, I'm sorry. I started copying down the same thing again. Here, let me go at that again. Negative r squared times k times q1 times q3. Set that equal to the other side, so we'll be multiplying by 0.185 plus r squared times k times quantity of charge 2 times quantity of charge 3. And that accounts for all of these different guys we just cross multiplied. Now we'll see some things happen right here that are kind of nice to work with. We'll notice that we have a charge, our q3 on both sides, so we can cancel those guys out, and we also have a k on both sides. We'll go ahead and cancel those k's out. So what this boils down to is negative q1 times r squared equaling q2 times 0.185 meters plus r meters squared. Okay, so we're about ready to plug in some of our charges and actually evaluate this. Obviously we're solving for r, and so I'll go ahead and plug in q1, which is 7.7 times 10 to the negative 6, negative 7.7 times 10 to the negative 6. That's multiplied by r squared equals q2, which is negative 3.5 times 10 to the negative 6th, and that's multiplied by 0.185 plus r squared. Moving right down the line, we can go ahead and cancel out these two 10 to the negative 6's. It just appears on both sides, and it's only bound by a multiplication, so we can take those guys out. And following that, we can multiply out or expand this 0.185 plus r squared, just good old-fashioned foiling. And that'll bring us to 7.7 times r squared equals 3.5, and that's a negative. These guys are both negative. Sorry, I just switched the signs on us. And that's r squared plus 1.295 r plus 0.119788. That's more decimals than we need to go, but add a little bit of precision. And then we can go ahead and move over this guy and subtract it over to here. That'll bring us to 0 equals 4.2r squared plus 1.295 r plus 0.119788. And we can just use the quadratic formula, or you can throw that in a calculator and solve for the zeros of this equation, and what you'll come out with is r equals negative 0.745, or r can equal 0.382833 meters. Both of these guys are meters, and if you go through and check the units, they'll all cancel out and come down to meters as well. Now, we're not going to have a negative distance. We remember that back from in elementary school, or middle school, I guess. And so that rules out this answer, and we're left with 0.3828 meters. And this distance, as we defined up here, is distance from this negative charge. So it's a distance beyond the negative charge, so not towards the positive charge, or that would upset the whole ordeal. I hope you enjoyed this and learned from it, and I'll see you guys next week. Oh, I blocked out my answer a little bit here. I can show you the rest of this work if you need to keep looking at that. Feel free to pause the video here. See you guys.